So in this video, I'm going to continue and finalize my practice questions for grade 12 advanced. We're going to focus on the focused IPQs, funnily enough, and this is related to the energy levels and spectra and stuff. So I've got a little lambda here, and if I delete it, I accidentally bring up the answers, so I don't know how I managed to get myself in that position, so ignore that for now. We need to find the wavelength of a photon with the energy of this much. So we're given an energy, we need a wavelength, and we know there is a relationship between the two. E equals hc over lambda. That's the formula that we're supposed to use. That's a terrible lambda. There we go. That's still bad. Now, what I need to do is find lambda. Energy must be in joules. This is in joules, so we can go ahead and use it. I can shift solve or rearrange. Rearranging is easy, by the way. You can just swap these around, swap them around, I should say. I will do hc over my energy. And I can just put the numbers in. This is 6.63. It's given to you on the front page, so you don't need to worry about it. 6.63, I don't know there. 6.63 times 10 to the minus 34, and I have not forward planned, I've ran out of space, multiplied by c, that's the speed of light. The speed of light is 3 times 10 to the power of 8 meters per second, and then I'm going to divide all of that by the energy, which is here, 1.44 times 10 to the minus 19. So apologies for the lack of space. And if I put that into my calculator and solve it, I am hoping I will get something like 1.38 times 10 to the minus 6 meters. Very nice. The energy in EV, if you have this wavelength over here, so this is a two-step solution now. We need to find the energy first, and then we will convert it to electron volts. So we'll use the same formula as given a wavelength, so I will do equals hc over lambda. If I had the frequency, I can just use E equals hf. But in this case, we have to use the other one with the wavelength inside. E equals hc over lambda. This is step number 1. I will do the same thing. This time I have more space, which is nice. 6.63 times 10 to the minus 34. I'm going to multiply that by 3 times 10 to the 8. And then I'm going to divide all of that by the lambda, which is a wavelength. That's 620 nano. 620 nano. That's times 10 to the minus 9. That's nano 9. Okay, very nice. After this, what we can do is solve it, get the number for this one, and if I was to do that, I should get something like 3.2 times 10 to the minus 19 joules. Perfect. Step 1 is done. That's supposed to be a 1. Step 2 is now converted to EV. Joules into EV. Electron volts. Remember electron volts? That is the charge of one electron passing through 1 volt. The work done to make one electron pass through 1 volt. And we know the charge of an electron. The charge of an electron was 1.6 times 10 to the minus 19. So all I need to do is take my number and divide it by 1.6. That's it. 3.2 times 10 to the minus 19. I'm going to divide that by 1.6 times 10 to the minus 19. And this will be electron volts. Cancel, cancel. That becomes 2. 2 EV. Just do it in the calculator. It's fine. So that's 2 electron volts. Very nice. So you just divide. If you want to put it into electron volts, you divide by 1.6. If you want to put it into joules, then you times by 1.6. Joules, W, or energy, is QV. Q, 1.6 times the V. That's why we're doing it. Anyway, not important. There you go. Now you know what to do. Which type of photon is emitted when an electron in a hydrogen atom drops from N2 to N1? Okay. Where it comes from doesn't matter. It's where it ends at. This is important. What type of photon is important to where it ends at. You need to know a few things. The ending, like for example, this is the different energy levels, and there are different series and different things associated with the series. Actually, what we can do is we can jump back to a previous page where we solved some of this. I'll quickly show you the relationship right here. This is the relationship. If you have Lyman series, that is ultraviolet light. Lyman series has the highest energy, and that's ultraviolet. And that drops at n equals 1. Then you have the Balmer series, which is visible light. And everything else is infrared. The passion, the bracket, the fun, that's all infrared. So that's what you need to know. These are the main ones. The main ones you'll actually deal with is Balmer and Lyman, to be honest. This is what you get asked about more. So if I was to go back to my question, I'm going to skip across to this one here. If I end wherever I started from, don't care where I started from, I end in here, this is Lyman and this is ultraviolet light. Every single time, okay? If I start from anywhere at all, it doesn't matter, but I finish here, this is going to be Balmer, I'm just going to write B, Balmer, and that is visible light that we can see. Different colors of light will come out. And then, similar, doesn't matter where I start, if I end at 3, this is the Passion series, and this is all going to be infrared. This will be infrared, so less energy than ultraviolet, of course. And then if we end at 4, so that just takes me from anywhere until 4, this one is called the Fund series. It's also PF, okay? And this is also infrared. Both of them is infrared. So keep that in mind. If it says dropping to n equals 1, then you know that is going to be Lyman or ultraviolet, depending on what the question is asking for. In this case, the question is saying ultraviolet, visible, infrared, radio wave, so I'm going to pick ultraviolet because that's related with Lyman. That helps us. Now, heading on to this question, I'll probably just get rid of all this stuff here. There we go. And let's see. What is the energy in electron volts of this emitted photon? So this happens when an electron drops. It's going to drop from where? From 3 to 2. It drops from 3 to 2. As it drops, it loses energy because if it absorbs energy, it will go up. If it loses energy, it will go down. And the only way it's going to do that is to release energy in the form of a photon. It's going to spit out energy in the form of a photon. Then it can come down and lose some of that energy. And once it go down again, it will spit out another photon. So it's given out a photon, and now we need to find the energy of that. And that's easy. This is going to be the energy that I'm going to figure out. It's actually E initial minus E final. It's not final minus initial like we always do, because that's normally helping you find the change of something. In this case, there's not a change of anything. I am releasing energy. I started with an amount of energy, and I released some energy, so I have less energy. So it's whatever I started with minus whatever I finished with, that tells me how much I released. Initial minus final. So just remember that. This is the only time we're going to use initial minus final. So let's do it. Minus 1.51 minus negative 3.39, and if I stick that into my calculator, we should get our answer. 1.51 minus negative 3.39, and I should get 1.88. 1.88. What have I done? 88 electron volts. Now I need to switch this into joules. If you remember what I said, if you want to go from electron volts into joules, how to do it, I will do EV. I'm just going to write it out here. EV2 joules. And if I want to switch it to joules, do I multiply or do I divide? From electron volts into joules, I will multiply. Electron volts are usually small numbers, by the way, and there's not normally a times 10 to the minus next to it. It's usually like this. So joules is the one that has the times 10 and all the different numbers, usually. So in our situation in grade 12, just remember that. If you're going to have a final answer and it's going to end up kind of small, that should be EV. If I have a times 10 next to it, then it should be joules. So I will take 1.88 times 10 to the minus 19, and that is hopefully going to get me. No, I've done that wrong. I'm being so silly. 1.8 times 1.6 times 10 to the minus 19. That's what I'm going to do. Now I'm going to go from electron volts into joules. So let's do that. 1.88 times 1.6 times 10 to the minus 19. 3 times 10 times 10 to the minus 19. That looks nice. That looks about right. Okay. 3 times 10 to the minus 19. Find the frequency of the emitted photon. The frequency is E equals HF. We can do this one because we have the E, not G. E equals HF. This is the rule. And you can shift solve. I'll rearrange. F equals E over H. I'm going to rearrange. E, I have it. I just used it. 3 times 10 to the minus 19. And I'm going to divide that by H. 6.63 times 10 to the minus 34. So let's get that into our calculator and see what the answer will be. I've got my answer written, so we'll divide that by 6.63 times 10 to the minus 34. And I will get 4.534. Why is this not working? 4.536. I'll round that to 4. I'll round it up. 36, that rounds up to 4. 4.54 times 10 to the 14 hertz. Wavelength of the emitted radiation. Great. Wavelength, if you remember the wave equation, funnily enough, I don't think this is given to you. Like I said, it helps you derive the hc over lambda formula, but it's simply wavelength is c over frequency. That's it. You can go ahead and do the hc over lambda, ahc over lambda. You're just working backwards again. You can do that and get the answer. It's fine. But I'm going to keep it simple. I'll just do 3 times 10. Both answers will be correct. Times 10 to the 8. And we'll divide that by my frequency, which is 4.54 times 10 to the 14. Now, sticking that into my calculator, I will do 3 times 10 to the power of 8. 3 times 10 to the power of 8 divided by my answer, and I will get 6.61. 6.61. Oh, what is this? 61 times 10 to the minus 7 meters. So don't need that. That is the final answer. Nicely done. Okay. Explain why this in the ground state can absorb this, but not this. Well, let's find out. If I'm in a ground state over here, and I want to absorb 10.2, that 10.2 will be the difference between one of these states. So final minus initial. So if I was to try, I will have to figure out how much energy is needed to get to this one, and then maybe this one, and then this one, and this one, just to see. 10.2. Let's see. Negative 13.58 minus negative 3.39, that is 10.19. So this one is basically telling me I can go here, 10.2 EV, the difference here. This minus this is a difference. However, if I said 11 electron volts, let's see where that would go. The next level up has to be the exact difference between here and here. These are fixed energy levels. If I am given a photon and I was given 10.1, 10.3, 10.2, there's only one of them that's going to get through, the 10.2. This one will take me to this stage. The other ones will be ignored. Similarly, with the 11 electron volt, I'm assuming now, in this case, the electron volts, this is not a difference in energy level. It will not absorb it. The next one up, let's just check. Let's do it. Minus 13.58 minus negative 1.51. That is 12.07. In order to get from here to the second state, I need a difference of 12.07. That means I now realized that 11 volts is somewhere in between 10 and 12. Not enough. Nothing will change. So to explain it, it needs to, well, writing it, let's leave it. There we go. It needs to have the exact difference between the energy levels. So very good. Okay. A hydrogen atom, initially at 2, is excited until he gets to 4. So if he's excited, remember, if he ends up jumping up, let me erase this stuff now. If he jumps up, that means he has gained energy. He is from 2, he went up, he absorbed energy. If he comes down, he emits energy. So straight away I'm going to ignore B and I'm going to ignore D. Now, this energy change, because it has, now we just need to find the difference between the two. Final minus initial we can do minus 0.8, I'll write it down right here. 0.85, minus, in a bracket I should probably, and then this is 3.39. 3.39. Close that over, and if I put that into the calculator, negative 0.85 minus negative 3.39, I should get 2.54 equals 2.54 EV. So I've written the answer up here, and 2.54 doesn't matter, it's multiple choice, and that's the closest answer. Very nice. And last question, what is the minimum energy needed to ionize a hydrogen in an N equals 2 state? Minimum energy needed. So what this is just saying is ionizing means I am leaving. This electron is escaping. That's what happens when you ionize. It escapes the atom. The minimum energy I need is the difference between here and the ionization level. This is 0, this is 3.39. I need a minimum of 3.39. So if I have 3.39, the electron will escape. Anything more than 3.39, at this point, it will all be converted to kinetic energy. It will move away faster afterwards. It can transfer. So the minimum energy I need is 3.39, and anything extra, it will be kinetic energy in this case. So that means the answer is C, and we are done. Thank you.